Hello guys, welcome to this new video. So now we are going to go through question 6 in the May 22 time zone 2 paper 2. So here we are investigating simple harmonic motion with a mass oscillating at the end of a vertical spring, and we have this motion sensor, and we conduct this experiment with a 1 kilogram mass and a 2 kilogram mass. And in the first one we had a spring constant of K1, and the other one we had a spring constant of K2, and we are given the speed of the masses for one cycle of the oscillation. And firstly, we need to calculate the frequency of the oscillation for both tests. Well, from this graph, we can see the period. So the period will just be when the object returns to the same positive speed. So as we can see for both tests, the period remained unchanged of 0.8 seconds. So from the graph, we can read off that t is equal to 0.8. And we know that the frequency is just 1 over the period. So 1 over 0.8 is equal to 1.25 hertz, or approximately 1.3 hertz. And then we need to deduce the ratio of K1 over K2. And well, for this, we can use the formula for the period of a mass oscillating on a spring, which, if we look in our data booklet, is this formula. And we also know that T1 will be equal to T2. As for the two tests, the period is the same of 0.8. So we can say that 2 pi times the root of M1 divided by K1 is equal to 2 pi times the root of M2 divided by K2. Like this. So like this, the 2 pi's cancel and the square root also cancels. So we are just left with M1 over K1 is equal to M2 over K2. And what we need is K1 over K2. So we can just bring the M2 down here and the K1 up here. And well, we know that M1 was 1 kilograms and M2 was 4 kilograms. So this will just be 1 over 4. So the spring constant of the second spring is 4 times as large. And then we need to determine the amplitude of oscillation for test 1. So for this smaller amplitude oscillation, well, we don't know this. We don't know whether it's smaller or not. We just see that the maximum speed is going to be smaller. So we can read off the graph that the maximum speed is approximately, well, if we look here, that is like 4.8, let's say. Is a little bit above, would be halfway, which would be 5. So 4.8, we know the maximum speed. So V max is equal to 4.8 meters per second. And we know that the maximum speed for an oscillation like this occurs when the mass is at the middle of the oscillation, as that's when it has zero potential energy and therefore a maximum kinetic energy, as the energy remains constant throughout an oscillation. So at x is equal to 0, x for displacement. And well, we can use the formula from our data booklet, which says that the speed is equal to the angular speed times the square root of our maximum amplitude squared minus our displacement squared. So this formula gives us the speed at a specific displacement. And well, we know that the speed is 4.8. We can calculate the angular speed, as we know our frequency, and we know angular speed is just 2 pi f. So this will just be, or it's just 2 pi over t, which was just 0.8, like this. And well, we know that this was just 0, as we want this, this speed is at when displacement is, displacement is equal to 0. So we're just left with another x0. And so from this, we can calculate that the maximum amplitude is 0.61 meters. And then we are told that in test 2, the maximum elastic potential energy stored is 44 joules. When t is equal to 0, the value of EP for test 2 is 0. So we already know that we're going to start at the origin, as potential energy is 0 at t equals 0. And we need to sketch on the axis the variation of this potential energy for test 2. So if we know the shape of this graph, this is a very simple question, but we can also think about this logically. So if our initial potential energy is 0, that means that we are actually at the middle, as we must know that for a oscillation like this, the energy remains constant. This is not damped or anything, so the oscillation must have constant energy of 44 joules. So that should be around over here. This is approximately 44 joules. So if we would draw both the kinetic and the potential energy graphs, at every time interval, they would add up to 44 joules. But now we only have to draw down this E potential. So at the start it has 0, so we know that the kinetic energy would be at a maximum. And then we let the mass oscillate. So what will happen is that it will go down to the bottom position, to the lowest position. It will do this in a quarter of the period. And at this moment, we have 0 kinetic energy, as it has just stopped, and therefore we will have maximum potential energy. So a fourth of the period will have to be 44 joules. So that's at 0.2 seconds. And then after another fourth of the period, it will go back up to the center position. And in this case, we will have the same situation. So we will have 0 potential energy as we're at the middle and maximum kinetic energy. And then it will go up in another t over 4 seconds. I'll draw this on the left. So t over 4 seconds. And again, here it will have maximum kinetic energy and 0 potential energy. And then finally, it will come back down to complete a full revolution in another fourth of the period, where again it will have 0 potential energy. So we just need to connect these dots in some form of a parabolic shape, as it is kind of expected of us to know that this will be the shape. We can derive this relationship, but it's not really needed. So generally, IB likes to ask this question because many people tend to forget. People think that it will just look like one sine wave, as that's what they're used to when looking at simple harmonic oscillations. But in fact, we need to remember that the potential energy becomes a maximum 2 times during our oscillation in one revolution. And then part B, we are told that the sensor operates by detecting the sound waves reflected from the base of the mass. The sensor compares the frequency detected with the frequency emitted when the signal returns. We're given that the frequency emitted is 35 kilohertz and we're given the speed of sound. And we need to determine the maximum frequency change detected by the sensor for test 2. So this is going to be about the Doppler effect, as we are dealing with changes of frequencies, and when sources and observers have changing like a different speed relative to each other, they will observe the Doppler effect. So the observed frequency will change. This is the Doppler effect. So this is a little bit tricky. We need to think about this because, well, first of all, usually when IB gives us a Doppler effect question, there's a good chance it will not just be using the formula once. That would be a little bit too simple. Plus, we see it's 4 marks. So let's see what's going on here. So first of all, the maximum frequency change will be detected when our block is moving at its maximum speed, Vmax. And since we're at test 2, we have to again see what our maximum speed is. If we look over here, that is about 9.4, I would say. If you look more closely, you can see it's approximately 9.4. So Vmax is equal to 9.4. So the biggest change in frequency is observed when we have our maximum speed. As we will see in our formulas, this speed is important. So if our sensor is over here, and it's measuring the sound waves, so it sends out some sound waves, and then the sound waves return, and from this it can calculate the speed. But what we need to see is that there are 2 Doppler effects going to happen here. So first of all, the sound wave is being sent out here. And in this situation, our source is stationary. So stationary source. But our block is moving down, right? It has a speed downwards. So it will have a moving observer. And then this sound wave still has to be reflected back down so that the machine can detect this frequency. And well, in this case, what we'll have is a moving source, as our block now becomes the source of the sound waves. So this purple sound wave originates on our block, and we will have a stationary observer, as our observer now. So this machine will just, it's stationary, so it will be not moving anymore, and it will just detect simply the frequency observer. So we need, so this Doppler effect kind of compounds up into these two situations, and we need to take both into account. Well, luckily, taking them into account is a little bit simpler than recognizing that this is happening, as we can just deal with both and then combine the frequencies. So first of all, we can deal with this green situation, so stationary source, moving observer. So whenever we have a moving observer, the formula that we can use is f prime is equal to f times v plus or minus u0 over v. And well, we can think about whether we need to use the plus or the minus sign. Since our block is moving downwards, the observed frequency will be a little bit larger, as this sound wave emits waves like this, and it's crossing them this way, so it will observe these green sound waves a little bit more frequently. So our frequency will have increased when it lands on the block. And well, the way for this f prime to increase is if we multiply this f by a number that is larger than 1. And the only way it can be larger than 1 is if we use the plus sign. And if we use the minus sign, then the top would be smaller. And so we know that we will have to use the formula of f times v plus mu 0 over v, like this. And then we can also take into account now the purple situation. So now we're going to have a moving source. So the formula we're going to have is, let's say, well, now the original frequency will be the frequency that was arriving at the block, as that changed frequency sound will be reflected back down. So let's say that our new frequency is going to be f prime prime, what is observed by our sensor, and our initial frequency was f prime, as that was what landed on the block, and then it will be v over v plus or minus mu 0. And again, we can consider whether its frequency will be larger than or smaller than. And since our block is moving downwards again, it will kind of compress the sound waves a little bit more. So the observed frequency will be a little bit larger by the sensor. So the only way that's possible is if we take the negative sign here, as then again, the top will be larger than the bottom. So we'll have a number larger than 1 here. So we'll just have f prime times v over v minus mu 0. And now we know what f prime is, right? We know that f prime is just this. So this is how we calculate f prime. So we can plug it back in. So we can say that our f prime prime will be our original frequency times v plus mu 0 over v times v over v minus mu 0. If we just plug everything in, we see that the v cancels out. So this we don't need to take into account. And so we just plug everything in. So our original frequency was 35 times 10 to the 3 hertz. And then we need to do v plus mu 0. So our speed of sound is 340 plus our speed of the block, 9.4, divided by 340 minus 9.4. And if we do this, we get 37 times 10 to the 3 hertz. So therefore the change will be the difference between 37 and 35. So that will be 2 kilohertz, or 2 times 10 to the 3 hertz. And well, this is the maximum frequency change. So yeah, this question was not so simple. You had to recognize multiple things. Firstly, that the biggest change occurs when our speed is the maximum, as that's when we add and subtract the largest numbers. So that's when our f prime prime will be the biggest. And you also have to see that the Doppler effect indeed happens twice, as the sound wave first has to travel to the block and then back to the sensor. And in both cases, we have a relative speed difference, and therefore a Doppler effect will happen in both instances. So this was question 6. I hope I was able to help in solving this problem, and see you in the next video.